So I wanted to make a little video to try to supplement Chapter 2, which is this guy, because I thought some pictures are missing. So let's get started. These are the slit planes. A slit plane is just the plane with a ray removed. So here I've removed the negative real axis, here I've removed the positive real axis, here I've removed a ray of angle alpha. I'm going to use C sub alpha as a notation for that, which will be convenient for us today. Now, so these are used in connection with selecting a choice of a local inverse, or if you like to think about it a different way, taking a branch cut of a multiply valued function. Multiply valued function, hey, wait a minute, is that a function? Okay, so let's talk about it here. So z squared. If we look at the square function, and we can think about restricting the square function to the upper half plane with the real axis not included. Well, the real axis itself would map to the positive real axis under the square function, right? Because the square of a positive number is a positive number, the square of a negative number is a negative number. They both map to this guy. So if we exclude the real axis, then we exclude the positive real axis in the image of the square function. So if we make the domain of the z squared function smaller, just the upper blue part, then we have injectivity. We have 1-to-1, which means we can find an inverse, and we can find a formula for that inverse using the right choice of the argument. All right, so if we use arg sub naught, that means that the angle is going to go from 0 to 2 pi. So if we divide by 2, we get angles going from 0 to pi, which means it makes sense. It's up here, and we've got the right thing. So if we square this, what happens is we get back w and e to the I arg naught of w. In other words, if you square this, you get back to w, which is what you want, right? That would make it an inverse function. This undoes the squaring. This undoes the squaring function. And so I have the gory details down here in purple. Also in purple is the fact that if you square and then take the inverse function, you also get back to z again. And here there's kind of a subtle point, which is that if you were taking arg sub naught of z squared, if instead of having arg naught, you had like arg of z squared here. Let's suppose you just had the principal argument. Well, z squared, if you study it, if z is coming from u plus, that means that z is taking, if we write z is equal to modulus of z times e to the I theta, well then the principal argument is ranging from what? I suppose from 0 to pi. But the 2 times theta is ranging from 0 to 2 pi, right? And if we calculated the principal argument of z squared, we wouldn't get 0 to 2 pi. We would get 0 to pi and then also 0 to minus pi, and then that would mess up this calculation. So it's kind of subtle, but it's important that we use arg naught for this calculation to make sense. All right. Moving on, though, of course, you could also flip it over. You could restrict the square function to the lower half plane. And this is part of a more generic pattern. If we take the z squared function and restrict it to an open half plane, its image is going to be a slit plane. Now I'm assuming really open half plane. In other words, this edge is not included. If we include the edge, we'll actually cover the whole plane, but then we'll lose what's called continuity. And we don't want to do that. More on that later. So lower half plane u minus maps to this. Again, we lose the same branch. We lose the same slit plane as an image. The formula in this case we could write in terms of our minus 2 pi of w over 2 like this. This would be a formula for the inverse of the square function going from here back to here. All right. But of course, you could just as well write minus that. Essentially, you could just kind of use the last example and add a minus because you flipped it over, you know. And you can check that this makes sense also. All right, so I was like, well, let's do it. Let's try to think about this for an arbitrary angle for the square function. So if I go from angle alpha and then sweep over to angle alpha plus pi, that gives me an open half plane like this. And then if you look at the square function, where does the square function take this line here? Well, it takes it not to alpha, but if you square this, you actually end up going to 2 alpha over here, right? So this is actually at theta equals to 2 alpha in the image. And so, like I said, the image of u alpha, which I'm calling this blue area, the image of u alpha is c2 alpha. And it's natural to use an angle, the argument, arg sub 2 alpha, because that ranges from 2 alpha to 2 alpha plus 2 pi. And so I'll use that to construct the local inverse for the square function on this slit plane by this formula. And again, you can check that it works. But the key point here is that since w is in the slit plane with 2 alpha missing, that means we can say 2 alpha less than arg 2 alpha w less than 2 alpha plus 2 pi. If we divide that by 2, we get alpha less than arg 2 alpha over 2 less than alpha plus pi. And that is the angle that's present in this formula, right? We would like, what we want, right, is that inverse function, it had better end up landing in the u alpha set, and that's exactly what it does, because the angle ranges between alpha and alpha plus pi, which is what we find in the desired restricted domain. So that's the square function. Moving on, the cube function. Well, the cube function, it takes the complex plane and it maps it to the complex plane, but embarrassingly, it does it 3 times, right? And so in order to get an invertible function for the cube function, we have to restrict the domain to like 1/3 of the complex plane. Something like this blue set, which I'm going to call u sub naught. So here f of z is z cubed. And again, we map 0 and 2 pi over 3 to the positive real axis. The inverse function then we can construct using the arg sub naught, just like we did before. So the inverse function here would be the cube root of the modulus of w, e to the I over 3 arg naught of w. And so what this function is doing is it's taking this slit complex plane and mapping it back to that 1/3 of the complex plane, again with the edges missing. All right. So notice, critical features here of this formula is that for the w over here, the angle's between 0 and 2 pi, right, as long as I use the arg sub naught. And we don't actually hit, even though arg naught of w could be 0, if we were feeding it the actual real axis, positive real axis, that's excluded, so that angle's not reached for arg naught of w. So long and short of it is that 0 is less than arg naught of w over 3, which is less than 2 pi over 3, which is to say that that kind of angle is precisely what we need for z, right? The idea here is that the inverse image of w should be equal to z, right? That's, we want f of z equal to w, and now I've used f here, but, to be more pedantic, I guess it's f restricted to, I can't write it in there worth anything, fine, I'll do it. F restricted to u naught of z equal to w, then f inverse of f restricted to u naught inverse of w is equal to z. So much to say. All right. Anyway, this is the construction of a local inverse for the cube function, right? But another way to say this is we're looking at, if you look at w to the 1/3, right, that's a set of, what is that? That has 3 values in it, right? So, it has 3 values. So we're selecting one of those values at the moment in this construction, right? And we're calling that value f restricted to u naught inverse of w. Anyway, I'm going to move on here. So then I thought, okay, well, how about an arbitrary angle? Oh, no, actually, sorry. My bad. I did not do an arbitrary angle. I decided to do what we often do, which is use the principal argument in the construction of an inverse. Now, when we use the principal argument in the construction of an inverse, it's usually based on the slit plane being the missing the negative real axis, all right? So if we're missing the negative real axis, of course, the angle ranges what? From minus pi over to pi, right? That's the deal with the principal argument. And if we exclude the negative real axis, we never actually hit pi, right? Pi is excluded. So that corresponds to actually restricting the cube function to this sector, this third of the complex plane, going from minus pi over 3 to pi over 3 angle. Here's the formula for the inverse function of the cube function with respect to this restriction. We take the cube root of the modulus, we take e to the principal argument of w over 3. And this is so important it has a name. This has a privileged notation. We say that this is the hey, es no bueno. It's just the principal third root, right? So there's no pesky modulus signs in here. It's just w in there, my friends. There we go. So that is yet another way we could find a local inverse for the cube. You're like, wait a minute, are there infinitely many ways to find a local inverse for the cube? Yes, there are infinitely many ways. So here's yet another way. So if I just start at angle alpha and then go alpha plus 2 pi over 3, get that third of the complex plane with the edge missing again, well, under the cube function, that's going to map to the slit complex plane missing the 3 alpha ray, like so. So again, theta equals 3 alpha ray deleted, and you won't be surprised. Well, maybe you'll still be surprised. I don't know. At some point, I wasn't surprised. I think it was about the 5th page I got bored. If w is in C sub 3 alpha, then that means 3 alpha is less than arg 3 alpha, and w is less than 3 alpha plus 2 pi by construction of arg 3 alpha. Hence, if we divide by 3, we've got alpha less than that, which means that this angle right here is precisely the angle of a point like z. This is the kind of angle we want to land in here, right? So it follows that we can write the inverse function for the cube here as, let's see if I can, I'm not sure I can fit it all in the same, I'm not sure if my zoom out enough. Oh yeah, it does fit. Okay, great. Move it up just ever so slightly. So the inverse function for the cube with respect to this guy is the cube root of the modulus of w, e to the I over 3, arg 3 alpha of w. This will be, by construction, an element of u alpha, which is what we want. We want the slit complex plane to map back to this, right? The range of the restriction should be the domain of the local inverse, and vice versa. All right. And then here is just me suffering through, well, I don't know, suffering, but, you know, f of f inverse of w is this, which is that, which is w, and the other way around also works, so. All right. Looking ahead then, we will talk about continuity next week, most likely. But we have some issues to settle about limits and topology and such before we get there, but we'll get there. And the issue here, why don't we use, you know, why am I deleting, I'm not using the full argument, right? The argument goes, you know, 0 to 2 pi, where 0 is included and 2 pi is not, or it goes from minus pi to pi, where pi is included for the principal argument. We get, you know, but I haven't been including one of those edges. And the reason for that is as follows. If we were to include it, right, and you could, f of z equals z cubed has f inverse of w equals the cube root of w. This is a principal cube root of w. For w and c, provided we define the domain of f to be not an open third plane, but it's neither open nor closed. It's something else. We'll learn what those words mean soon, but for the moment I'm just using them. You probably know what it means intuitively though, right? So you notice I've included that edge, and that edge maps to the missing, what was slit before. And so we cover the whole. It's still an inverse function. I mean, that's not wrong. It's just the trouble is, if you study how the inverse function behaves as you approach this point here, you get this weird jump in the outputs from minus pi over 3 to pi over 3, and that is you know, a signature discontinuity in the principal third root. If we were to extend it to the whole complex plane, we get into trouble right there in terms of continuity. And that's going to be an issue because we're ultimately interested in studying complex differentiability, and you may recall from real differentiability implies continuity. So, you know, if we lose continuity, we've certainly also lost differentiability, and so we're just a thought. All right. Likewise, same issue for the square function. If we were to extend this, we do define the principal square root for the whole complex plane, right? But we can't have a continuous principal square root for the whole complex plane because of the angle jump. We have the angle jump at the negative real axis. We jump from outputs of minus pi to outputs like pi. Well, actually, technically the angle out is minus pi over 2 and pi over 2 over here. But there's a discontinuity in the output of the square root as you jump, as you go along there. All right. So the problem is continuity. That's why we have to use a slit complex plane to avoid the discontinuity of the inverse function across the slit. All right. Next, the fourth power. So the fourth power is a local. We can look at local inverses for the fourth power function. And so here I've done the principal fourth root. It is, the principal fourth root. If we want a continuous principal fourth root, we have to restrict to the slit complex plane. I'm missing the negative real axis. I called that C minus, of course. And maybe I had the minus up. I forgot at this point. If you don't like that, we could say C pi or C minus pi, whatever, in my other language. Now, so then the inverse function, this would be the domain of the inverse for the fourth power function, and the formula is given by the principal argument as follows. So f restricted to this quarter plane, open quarter plane, which I've called u minus pi over 4 because minus pi over 4 is its starting angle. That was my notation. That of w is going to be the fourth root of the modulus of w e to the I arg w over 4. And that's only going to be, of course, for w in the slit complex plane. So this is the principal fourth root function is continuous on the slit complex plane, and it serves as a local inverse for the fourth power function z to the fourth on the sector u minus pi over 4, which has standard angle ranging from minus pi over 4 to pi over 4. And of course you can generalize this, start at angle alpha, go to angle alpha plus 2 pi over 4, which is pi over 2, and you can find a local inverse with respect to this restriction in terms of taking a branch of the fourth root where the slit is where you cut it at angle 4 alpha. It's a branch cut of w to the 1/4 at theta equal to 4 alpha, whatever this lingo means. All right. Well, that was a loud hiccup. All right. Not me. So there you go. There's the formula for angle alpha. And here's the justification that if we use w in the slit complex plane and use that angle function, by construction we have that range of angles, which means when we divide by 4 we have this range of angles, which is precisely what we need for z, this is equal to z, right, to actually be there. And it is. All right, are you bored? I'm bored. Now the nth power function. F of z equals z to the n. Well, what's the story? Let's give a summary. The range of f is the whole complex plane, but if we set w equal to z to the n, in fact, we worked out somewhat carefully in class this week that z is an element of w to the 1 over n, and that this is a set of n values provided w is non-zero. So when we think about finding an inverse for f of z equals z to the n, we have to select one of those n values. That selection of one of those n values is what's called taking a branch cut. So here it is, the sort of principal nth root. Here's the picture for the principal nth root. We're taking, basically it's a local inverse for z to the n, and we're restricting to the sector from minus pi over n to pi over n, and then that the range of that is the slit complex plane, deleting the negative real axis, and here's the formula for you. Again, that has this is so special we give it a name. This is the nth root of w. All right. The standard choice of inverse, in much the same way that you choose sine inverse on your calculator to be what it is, or cosine inverse or tangent inverse. It's a choice. And then if we were to start at alpha, we could go to alpha plus 2 pi and find the local inverse with respect to that sector, and that would be corresponding to a cut at angle n alpha in the slit plane, a slit plane at n alpha. And the inverse is actually this. Again, you can check that this angle is necessarily falling in here like you want, provided that we're using the arg sub n alpha angle function over here. In conclusion, to make a branch cut of w to the 1 over n at beta, we use this for w and c beta. So I just put n alpha equal to beta just to kind of summarize what we did. So next, we should talk about the exponential function. So I am going to post a separate video for that because I foresee interruptions.